CFD analysis of double pipe counterflow heat exchanger. Abstract. The design of a double pipe and tube heat exchanger has been facing problems because of the lack of experimental data available regarding the behavior of fluid flow in double pipe and also in case of heat transfer data, which is not in the case in shell and tube heat exchanger. So to the best of our effort, double pipe heat exchanger by varying the different parameters like different temperatures and diameters of pipe and coil, and also to determine the fluid flow pattern in a double pipe heat exchanger. The objective of this project is to obtain a better and more quantitative insight into the heat transfer process that occurs when a fluid flows. The study also covered the different types of fluid flow range extending from laminar flow through the transition to the turbulent flow. The materials for the study were decided. Fluid taken was water and the material for the pipe was taken to be steel for its better conducting properties. Index term double pipe heat exchanger, CFD analysis, solution, results and discussion, conclusion, report. 1. Introduction. Heat exchange between flowing fluids is one of the most important physical process of concern, and a variety of heat exchangers are used in different types of installation, as in process industries, power plants, food processing, refrigeration, etc. The purpose of constructing a heat exchanger is to get an efficient method of heat transfer from one fluid to another, by direct contact or by indirect contact. The heat transfer occurs by three principles: conduction, convection, or radiation. In a heat exchanger, the heat transfer through the radiation is not taken into the account as it is negligible in comparison to conduction and convection. Conduction takes place when the heat from the higher temperature fluid flows through the surrounding solid wall. The conductive heat transfer can be maximized by selecting a minimum thickness of wall of a highly conductive material. But convection plays an important role in the performance of a heat exchanger. Forced convection in a heat exchanger transfers heat from one moving stream to another stream through the wall of the pipe. The cooler fluid removes heat from hotter fluid as it flows along or cross it. Different CO relation are used for the calculation for the Nusselt No and the heat transfer coefficient. 1.1. Double pipe heat exchanger. A typical double pipe heat exchanger consists of one pipe placed concentrically inside another larger diameter with appropriate fittings to direct the flow from one section to next. As shown in figure 1, double pipe heat exchanger can be arranged into various series and parallel arrangements to meet pressure drop and mean temperature difference requirements. The major use of double pipe heat exchanger is for sensible heating and cooling of process fluid where small heat transfer areas is required, up to 50 square meters. This configuration is also very suitable when one or both fluid are at high pressure. The major disadvantage is that double pipe heat exchanger are bulky and expensive per unit transfer surface. Inner tube may be single tube or multi-tube. If the heat transfer coefficient is poor for annulus, axially finned inner tubes can be used. Generally, double pipe heat exchanger are built in modular concept, i.e., in the form of hairpins. Study has been done on the type of the flows in the circular straight pipes, and the effect of Prandtl and Reynolds number on the flow patterns and on Nusselt numbers. The two basic boundary conditions that are faced in the applications are constant temperature and the constant heat flux of the wall. 1.2. Heat transfer coefficient. Convective heat transfer is the transfer of heat from one place to another by the movement of the fluids due to the difference in density across a film of the surrounding fluid over the hot surface. Through this film, heat transfer takes place by thermal conduction, and as thermal conductivity of most fluids is low, the main resistance lies there. Heat transfer through the film can be enhanced by increasing the velocity of the fluid flowing over the surface, which results in reduction in the thin film. The equation of the rate of heat transfer by convection under steady state is given by Q equals HA, TW tatum, where H is the film coefficient or surface coefficient, W/m2.K. A is the area of the wall. TW is the wall temperature. Tatum is the surrounding temperature. The value of H depends upon the properties of fluid within the film region, hence it is called heat transfer coefficient. It depends on various properties of fluid, linear dimensions of surface and fluid velocity, i.e., nature of flow. The overall heat transfer coefficient is the overall transfer rate of a series or parallel combination of convective and conductive walls. The overall heat transfer coefficient is expressed in terms of thermal resistances of each fluid stream. The summation of individual resistance is the total thermal resistance, and its inverse is the overall heat transfer coefficient U. 1/U equals 1/Ho plus AO/AI times 1/Hi plus AO/AI times RFI plus RW, where U equals overall heat transfer coefficient based on outside area of tube wall. A equals area of tube wall. H equals convective heat transfer coefficient. RF equals thermal resistance due to fouling. RW equals thermal resistance due to wall conduction. And suffixes O and I refer to the outer and inner tubes, respectively. 1.3 Advantages of double pipe heat exchanger. It is extremely easy to build and easy of operation. Its handle differential thermal expansions by the construction of the hairpin type component. The make use of longitudinal fin tubes, while having a low heat transfer coefficient. Easy to cleaning, maintenance, repair. Shortened delivery times can result from the use of stock components that can be assembled into standard sections. Modular design allows for the addition of sections at a later time or the rearrangement of the sections for new services. Simple construction leads to ease of cleaning, inspection, and tube element replacement. 1.4 Disadvantages of double pipe heat exchanger. Hairpin heat exchanger sections are specifically intended units which are generally not built to any manufacturing industry standard other than ASME code. However, TIMA tolerances are normally incorporated wherever applicable. Various hairpin heat exchanger sections are not at all times cost-effectively competitive with a distinct shell and tube heat exchanger. Proprietary closure design requires special gaskets. 1.5 Double pipe heat exchanger applications. 1 Pasteurization. 2 Digester. 3 Heat recovery. 4 Preheating. 5 Effluent cooling. 2. Literature review. Heat transfer enhancement in a heat exchanger is getting industrial importance because it gives the opportunity to reduce the heat transfer area for the heat exchanger. Increase in the heat exchanger performance can help to make energy, material, and cost saving related to a heat exchange process. Double pipe heat exchangers are the simplest devices in which the heat is transferred from the hot fluid to the cold fluid through a separating cylindrical wall. They are primarily adapted to high temperature and high pressure application due to their small diameters. They are fairly cheap, but the amount of space they occupy is relatively high compared to the other types. Hence, for the given design and the length of the heat exchanger, heat transfer enhancement in a double pipe heat exchanger is possibly achieved by several methods. Chen et al. Used dimples as the heat transfer modification on TH inner tube. We et al. Amson et al. and Lioa et al. Used circular tube equipped with perforated twisted tape inserts with the different configurations to enhance the heat transfer through the tubes. In order to intensify the heat transfer from the heat exchanger surface to fluids, it is possible to increase convection coefficient by growing the fluid velocity, widens temperature difference between surface and fluids, or increase the surface area across which the convection occurs. Extended surfaces, in the form of longitudinal or radical fins, are common applications where the need to enhance the heat transfer between a surface and an adjacent fluid exists. Several researchers used extended surfaces for the enhancement in the heat transfer. MASLIETAL studied heat transfer characteristics for a laminar forced convection fully developed flow in an internally trained Euler fin circular tube with axially uniform heat flux using a finite element method. For given fin geometry, the Nusselt number based on inside tube diameter was higher than that for a smooth tube. Also, it was found that for a maximum heat transfer there exists an optimum fin number for a given fin configuration. Agarwal et al. Studied laminar flow and heat transfer magnitudes in a fin tube annulus. Pressure drop and heat transfer characteristics of the fins are obtained in the periodically fully developed region by varying geometric and flow parameters. Geometric parameters are annulus radius ratio, 0.3 to 0.5, fin height / annular gap, 0.33 to 0.67, and fin spacing / annular gap, 2 to 5. Flow parameters are Reynolds number, 100 to 1000, and Prandtl number, 1 to 5. Comparison are made with a plain tube annulus having the same length heat transfer surface area volume flow rate and Reynolds number. They observed that a Prandtl number less than 2. The use of fin may not be justified because the increase in pressure drop is more pronounced than the increase in heat transfer. At a Reynolds number of 1000 and a Prandtl number of 5 the heat transfer increases by a factor of 3.1 while the pressure drop increases by a factor of 2.3. Soliman et al. Studied steady, laminar, forced convection heat transfer in the thermal entrance region of internally fin tubes for the case of fully hydrodynamics. Results were presented for 16 geometries including the local Nusselt number and developing length corresponding to each boundary condition. These results indicate that internal fining influences the thermal development in a complicated way which makes it inappropriate to extend the smooth tube results to internally fin tubes on a hydraulic diameter basis. Total et al. Conducted experiment in a double pipe heat exchanger by providing threads in the inner pipe. They observed that the Nusselt number heat transfer coefficient was increased for the threaded pipe, but the pumping power required also increased compared to the plain tube. Cannon et al. Studied that the heat transfer through the double pipe heat exchanger with annular fins. 3 different configurations annular ring, spiral rod, and the rectangular projection were considered on the outside surface of the outer tube. Experiments were done with varied mass flow rates. It was observed that heat transfer rate was increased for a fin tube. Fin with annular ring showed better performance than the other methods. Nagarani et al. Used circular and elliptical annular fins than the circular fins. Heat transfer coefficient depends on the fin spacing, flow condition, and fluid properties. Fin efficiency was higher for elliptical fins. Mir et al. Studied numerical simulation of the steady, laminar, forced convection heat transfer in the fin annulus for the case of fully developed incompressible region of fin double pipe subjected to constant heat flux boundary conditions. They found a significant enhancement in heat transfer rate and also Nusselt number. For small numbers of fins, fin geometries like fin height ratio of radii and half fin angle were found to be less influential. Iqbal et al. Investigated optimal configuration of fin annulus with parabolic, trained Euler, and trapezoidal fins using finite element methods and genetic algorithm. They concluded that no single fin shape is best in all situations and for all criteria. Zhang et al. Studied heat transfer enhancement for shell side of a double pipe heat exchanger with helical fins and pin fins. The three-dimensional velocity components for the shell side with and without the pin fins were measured experimentally using the Doppler anemometer, LDA, under cylindrical coordinate system and the fluid flow characteristics. The results show that for the shield side only the helical fins at large pitch there was a pair of vortex near the upper and the lower edge of the rectangular cross-section. Weakest secondary flow occurred at the center. By pin fins being installed the three-dimensional velocity components in the helical channel were strongly changed. Patel et al. Simulated the industrial experimental of a double pipe heat exchanger using NC 14 CFX. Results indicated heat transfer pressure drop, pumping power increased with mass flow rate whereas friction factor decreased. For heat exchangers, built with many fins and designed for real industry, it is important to pay attention to and calculate the heat transfer considering the fluid flow and flow paths. The resistance of the body results in a pressure drop. Literature survey reveals that most of the analysis was done by considering constant heat flux or constant wall temperature boundary condition. Literature regarding the numerical study of enhancement in the heat transfer characteristics using the different configurations of the internal longitudinal fins for a double pipe heat exchanger with the conjugate heat transfer is still scarce. Hence the present work aimed at the comparison of heat transfer characteristics using the different mass flow rates and the temperature for parallel and counter flow of a double pipe heat exchanger under various operating conditions to evolve with the best possible configurations. Numerical simulation was done using commercial CFD package. Heat transfer characteristics like temperature variations, heat transfer rate, and heat transfer coefficient for the above said models were compared and are presented. 3. Introduction to CFD. Study of fluid flow has been around for millennium, dating back to ancient Greece, but their understanding did not go beyond what they need to know to run aqueducts and other water works. Da Vinci further pursued the topic during the Renaissance, observing waves and free jets. Even Newton studied fluids. The topic did not mature until people like Bernoulli and Euler investigated it and developed the equations that were named after them. The Euler equations were further modified by Claude Mary Henry Navier and George Gabriel Stokes to create Navier-Stokes equation. These men laid the groundwork that would be the foundation of computational fluid dynamics. Computational fluid dynamics is a term to describe a way of modeling the fluids using algorithms and numerical methods. Currently they are solved utilizing computers, but early methods were completed manually without the aid of the computers. Computational fluid dynamics are a powerful tool to model fluids, but even with the most state-of-the-art supercomputers and technological advances they are only an approximation of what would occur in reality. It is unclear exactly when computational fluid dynamics came into being. Louis Fry Richardson attempted to predict the weather by creating a grid in physical space and using BJERKNE primitive differential equation. His method involved a stadium of 64,000 people each using a mechanical calculator to solve part of the flow equation. It ended in failure. In 1933 Atom was able to numerically compute flow past a cylinder. Another mechanical solution was made by K. Kawagiti which took 20 hours a week over 18 months. NASA's theoretical division also made contribution during 1960, but it was not until the 1980s when commercial methods for computational fluid dynamics became available. Fluid flow is classified as external and internal depending on whether the fluid is forced to flow over a surface or, in a conduit. Fluid flow in circular and non-circular is commonly encountered in practice. The hot and cold water that we use in our homes is pumped through pipes. Water in a city is distributed by extensive piping network. Oil and natural gas are transported hundreds of miles by large pipelines. Blood is carried through our bodies by arteries and veins. The cooling water in an engine is transported by hoses to the pipes and radiator where it is cooled as it flows. Thermal energy in a hydronic space heating system is transferred to the circulating water in the boiler and then it is transported to the desired location through the pipes. So, it can be seen that many of the industrial processes have to deal with the flow through pipe. If analysis and simulation of flow through the pipe is done well, then many of the industrial problems can be understood and solved using the results obtained. Hence, in this project incompressible flow through the double pipe hex is simulated using CFD code software and Fluent 17.1. 3.1 Computational fluid dynamics in Fluent. Computational fluid dynamics essentially means computational transport phenomenon which involves fluid dynamics, heat, and mass transfer or any phenomenon involving the transport phenomenon. CFD is about numerical simulation of governing equations for some transport. Computational fluid is applied in many fields of science like aerospace, biomedical, and automobile chemical industry, electronics, marine engineering, material processing, microfluids, turbo machines, etc. Fluent is a CFD code used for flow modeling applications. Fluent needs some input data and domain draws from various software like Gambit Kasha Pro E and other design software. Now Fluent can analyze the given domain with boundary conditions and solve the governing equations for the flow given the different parameters. Steps for analysis in the Fluent are: A. Pre-processing. It involves building a model or importing one from a CAD package, applying. B. Calculation. Once the numerical model is prepared, Fluent performs the necessary calculation and produces the desired model. C. Post-processing. It involves organization and interpolation of the data and images. It can handle transient and steady flow, laminar and turbulent flow, Newtonian and non-Newtonian fluid, single and multi-phase flow, chemical reactions including combination, flows through porous media, heat transfer, flow-induced vibration. This project and our research basically deals with turbulent flow of water through the double pipe. It also contains heat transfer and single-phase flow. 3.2 Basic principle that govern the implementation of CFD. Fundamental principles of conservation which governs the basic equation that we commonly used for CFD and not only CFD is analytical fluid dynamics are: continuity equation, a mass conservation equation. 3.3. Major key findings and gap analysis. The brief story of computational fluid dynamics can be shown. Until 1910, improvements on mathematical models and numerical methods. 1910 to 1940, integration of models and methods to generate numerical solutions based on hand calculations. 1940 to 1950, transition to computer-based calculations with early computers, ENIAC, solution for flow around cylinder by Coagudi with a mechanical desk calculator in 1953. 1950 to 1960, initial study using the computers to model fluid flow based on the Navier-Stokes equation by Los Alamas National Lab US. Evaluation of vorticity stream function method. First implementation for 2D, transient, incompressible flow in the world. 1960 to 1970, first scientific paper calculation of potential flow about arbitrary bodies was published about the computational analysis of 3D bodies by Hess and Smith in 1967. Generation of commercial codes. Contribution of various methods such K. Turbulent model, arbitrary Lagrangian Eulerian, simple algorithm which are all still broadly used. 1970 to 1980, codes generated by Boeing NASA and some have unveiled and started to use several yields such as submarines, surface ships and automobiles, helicopters and aircrafts. 1980 to 1990, improvement of accurate solution of transonic flows in three-dimensional case by James E.T.al. Commercial codes have started to implement through both the academia and industry. 1990 present, through the development in informatics, worldwide usage of CFD virtually in every sector. 4. CFD analysis. Computational fluid dynamics, CFD, is the study of the system starts with the construction of desired geometry and mesh for modeling the dominion. Generally, geometry is simplified for the CFD studies. Meshing is the degradation of the domain into small volumes where the equations are solved by the help of iterative methods. Modeling starts with the describing of the boundary and initial conditions for the dominion and leads to modeling of the entire system. Finally, it is followed by the analysis of the results, conclusions, and discussions. 4.1. Geometry. Heat exchanger is built in the ANSYS workbench design module. It is a counterflow heat exchanger. First, the fluid flow, Fluent, module from the workbench is selected. The design modeler opens as a new window as the geometry is double-clicked. 4.1.1. Sketching. Out of the three plane viz XY plane, YZ plane and ZX plane, the XY plane is selected for the first sketch. A circle of diameter 70 mm and another circle with diameter 66 mm is drawn by selecting the circle in sketching tab menu. Similarly by selecting again XY plane we draw another sketch with two circle having diameter 42 mm and 34 mm. 4.1.2. Extrude. By selecting the first sketch in XY plane extrude it up to a length of 1250 mm, name as a outer pipe. Again select another sketch, extrude it up to 1400 mm and name as inner pipe and change its operation from material to add frozen in Z direction and change operation add material to add frozen. By extruding the whole body and by changing operation from add material to add frozen we have 4 different parts and 4 bodies. 4.2. Mesh. Initially a relatively cover mesh is generated. This mesh contains mixed cells, tetra and hexahedral cells, having both triangular and quadrilateral faces at the boundaries. Care is taken to use structured hexahedral cells as much as possible. It is meant to reduce numerical diffusion as much as possible by structuring the mesh in a well manner, particularly near well region. Later on, a fine mesh is generated. For this fine mesh, the edges and region of high temperature and pressure gradients are finely meshed. 4.2.1. Y-end values. Y-end values plays a significant role in turbulence modeling for the near wall treatment. Y-end is a non-dimensional distance. It is frequently used to describe how coarse or fine a mesh is for a particular flow pattern. It determines the proper size of the cells near the domain walls. The turbulence model wall laws have limitations on the Y-end values at the wall. For instance, the standard K-epsilon model requires a wall Y-end value between approximately 300 and 100. A faster flow near the wall must be decreased. Y-end values for different wall treatments are given in Table 2. The mesh details gave us the following information. Relevance center fine meshing. Smoothing high. Size 0.747970 mm to 74.7970 mm. Nodes, 104, 5694. Elements, 703,592. 4.2.2 Name selection. The different surfaces of the solid are named as per required inlets and outlets for inner and outer fluids. The outer wall is named as insulation surface. Save project again at this point and close the window. Refresh and update project on the workbench. Now open the setup. The ANSYS Fluent launcher will open in a window. Set dimension as 3D, option as double precision, processing as serial type and hit OK. The Fluent window will open. 4.3 Solution. 4.3.1 Problem setup. The mesh is checked and quality is obtained. The analysis type is changed to pressure-based type. The velocity formulation is changed to absolute and time to steady state. Gravity is defined as y equals 9.81 m/s2. 4.3.2 Models. Energy is set to on positions. Viscous model is selected as K. Model. 4.3.3 Materials. The Create/Edit option is clicked to add water, liquid and copper to the list of fluid and solid respectively from the Fluent database. 4.3.4 Cell zone conditions. Inner and outer fluid assigned as water and inner and outer solid pipe assigned as material copper. 4.3.5 Boundary conditions. Boundary condition are used according to the need of the model. The inlet and outlet conditions are defined as mass flow inlet and pressure outlet. As this is a counterflow and parallel flow with two tubes as there are two inlets and two outlets. The walls are separately specified with respective boundary conditions. No slip conditions is considered for each wall. Except the tube walls, each wall is set to zero heat flux condition. The details about all boundary conditions can be seen in the table 3 as given below. 4.3.6 Reference value. The inner inlet is selected from the drop-down list of compute from. The values are: area equals 1 m2. Density equals 998.2 kg/m3. Length equals 1000 mm. Temperature equals 360 K. Velocity equals 0.28 m/s. Viscosity equals 0.001003 kg/ms. Ratio of specific heats equals 1.4. 4.3.7 Solution methods. The solution methods are specified as follows. Scheme equals simplex. Gradient equals least square cell based. Pressure equals standard. Momentum equals power law. Turbulent kinetic law equals power law. Turbulent dissipation rate equals power law. Energy equals second order upwind. 4.3.8 Solution control and initialization. Under relaxation factors the parameters are: pressure equals 0.3 Pascal. Density equals 1 kg/m3. Body forces equals 1 kg/m2s2. Momentum equals 0.7 kg/m/s. Turbulent kinetic energy equals 0.8 m2/s2. Then the solution initialization method is set to standard initialization, whereas the reference frame is set to relative cell zone. The inner inlet is selected from the compute from drop-down list and the solution is initialized. 4.3.9 Measure of Convergence. It is tried to have a nice convergence throughout the simulation, and hence criteria is made strict so as to get an accurate result. For this reason residuals are given as per the table 4 that follows. April 3, 10 run calculation. The number of iteration is set to 300 and the solution is calculated in various contours, vectors, and place are obtained. 5. Results in discussion. 5.1. Contours. The temperature, pressure, and velocity distribution along the heat exchanger can be seen through the contours. 7. Conclusion. A CFD package, ANSI Fluent 17.0, was used for the numerical study of heat transfer characteristics of a double pipe heat exchanger for counterflow, and the results was determined. The study showed the heat transfer within the error limits performance of counterflow configuration. Nusselt number at different points along the pipe length was determined from the numerical data. The simulation was carried out for water-to-water heat transfer characteristics and for same length and same diameter of tube and annulus for same input temperature for cold inlet 300 K, and for hot inlet 360 K. We analyzed that in counterflow heat exchanger there is high temperature difference in output streams, hot outlet, cold outlet. Nusselt number for the counterflow heat exchanger 802. For the given design and length of heat exchanger heat transfer enhancement in a double pipe heat exchanger is possible achieved by several methods. These techniques are divided into active and passive techniques. Active methods involve some external input for the enhancement of the heat transfer like induced vibrations, injections, and suctions of the fluids and jet impingement, etc. Another method is the passive method without the simulation by external power such as surface coating, surface roughness, and extended surfaces.